In this video, we continue our journey into cryptography, shifting our focus this time to asymmetric encryption algorithms. Today, we'll explore two of the most fundamental asymmetric cryptographic techniques, RSA and Diffie-Hellman. Asymmetric cryptography is a powerful approach to secure communication, relying on a pair of keys, one public and one private, to encrypt and decrypt data. Unlike symmetric encryption, which requires both parties to share a single secret key, asymmetric encryption eliminates the need for secure key exchange, making it ideal for applications like digital signatures, secure messaging, and key distribution. Throughout this video, we'll break down how RSA encryption secures data, how Diffie-Hellman enables security key exchange over an insecure channel, and the strengths and the weaknesses of asymmetric cryptography compared to symmetric methods. By the end of this video, you will have a solid understanding of how these encryption methods work and why they are crucial for modern cybersecurity. Let's begin by introducing RSA encryption, one of the most widely used asymmetric encryption algorithms. Unlike symmetric encryption, which relies on a single shared key, RSA operates with a pair of keys, a public key for encryption and a private key which is used for decryption. RSA's security is based on the mathematical challenge of factoring very large prime numbers. As computers struggle to break down these large numbers efficiently, RSA remains highly secure, making it an essential tool for data encryption, digital signatures, and secure authentication in the modern communication systems. While RSA provides strong security, it's computationally more demanding than symmetric encryption algorithms like advanced encryption standard. Despite this, RSA plays a crucial role in securing online transactions, protecting sensitive data, and verifying the authenticity of digital communications. Next, we'll break down how RSA encryption works, starting with the key generation. RSA begins with the generation of two large prime numbers represented as P and Q. These prime numbers are carefully chosen because their product forms the basis of RSA's security strength. Once we have these two numbers, we compute n, which becomes a part of both the public and private keys. The value n is crucial because it determines the complexity of breaking RSA encryption. Next, we compute Euler's totient function. This function is calculated as p minus 1 multiplied by q minus 1. Now we are able to select the public exponent e, which must meet two conditions. E must be less than the totient and greater than 1, and e must be coprime with the totient, meaning it shares no factors with the totient other than 1. The greatest common divisor between e and totient must equal 1. Coprime numbers are numbers that don't have any common divisors except for 1. Choosing the right e ensures that encryption functions correctly. Finally, we calculate the private exponent d using the equation e times d mod totient equal 1. This private key, dn, must remain secret, while the public key is shared openly for encryption. Now let's see how encryption works. To encrypt a message M, we use the public key, E and N, and apply the following formula. So the ciphertext equals the message raised to the power E mod N. This transforms the plain message or the plain text message into an encrypted ciphertext C, which can only be decrypted by the corresponding private key. When the intended recipient receives the ciphertext, they use the private key Dn to decrypt it. The decryption formula is C, which is the ciphertext, raised to the power D, which is part of the private key, mod N. This restores the original message M, ensuring that only the authorized recipient can read it. In this section, we'll walk through the RSA key generation process using simple numbers to understand how public and private keys are created. RSA encryption is based on the mathematical difficulty of factoring large prime numbers. Let's break it down step by step. The first step, selecting two large prime numbers. To generate RSA keys, we first need two prime numbers. For this example, let's choose P equal 2 and Q equal 7. These numbers are selected to keep the example simple, but in real-world applications, much larger primes, hundreds of digits long, are used to ensure security. Next, we calculate n, which is the product of our chosen primes. N equals p times q. That's why you see 14, which is the result by multiplying 2 times 7. Substituting the values 2 and 7, we get 14 as the value of n. And this will be used in both the public and private keys. It's used as the modulus for both encryption and decryption operations. Now we compute the Euler's totient function, which determines the number of integers less than n that are co-prime with n. The formula for the totient function is p minus 1 multiplied by q minus 1. Substituting our values, we get the totient equal 6. This value will be crucial in the next step when we choose the public exponent e. Now that we have calculated n equal 14 and the totient equals 6, the next step is to choose the public exponent e. To select e, we need to satisfy two key conditions. E must be greater than 1 but less than totient. That's the first condition, as you see. Again, so e must be greater than 1 and less than totient, which is in this case 6. And e must be co-prime with the totient. This means the greatest common divisor between e and 6, which is the totient, must equal 1. That means e and totient should have no common factors other than 1. Co-prime numbers, it's good to understand what they mean. A number is considered co-prime with another if the greatest common divisor, GCD, between them is 1. So let's check which numbers between 1 and 6 meets this condition. The numbers that fall within our valid range are 2, 3, 4, and 5. So if you look at the table on the screen, the values for e that I'll be checking are 2, 3, 4, 5, because this satisfies the first rule where e must be less than 6, the totient, and greater than 1. And then if you look at the second rule, the greatest common divisor between e and the totient, which is in our example is 6, must equal 1. So I can do this simply first by listing the factors of 6, which is the totient, which is above the table. The factors are 1, 2, 3, and 6. And then I list the factors for every e value. So the factors for 2 are 1, 2. The factors for 3 is 1, 3. The factors for 4 are 1, 2, and 4. The factors for 5 are 1 and 5. And then I find the common factors between e and the totient until I find the common factor, or the GCD, between them is 1. So if you look at 2, 3, and 4, these are not co-prime, because the greatest common divisor between the e, when it's 2, 3, and 4, and 6, which is the totient, it's 2, 3, and 2. So the greatest is not 1. So these are not co-prime. Until I found e equal 5, the greatest common divisor between 5 and our totient, which is 6 in this example, equals 1. So that's a co-prime. So I found my e. So now if you want to check, e equals 5. So 5 is greater than 1 and less than the totient 6. So in this case, it satisfies the first rule. And then if I look at the greatest common divisor between 5 and 6, it equals 1. So I did satisfy the second rule. So that could be used as e for the public key. So this completes the process of selecting the public key exponent for our RSA encryption. Next, we will calculate the private exponent d using the modular inverse of e mod totient. And here we see e equal 5. So the public key, now I have e and n, 5, 14. So this is the pair I'll use for my public key. Now that we have selected e equal 5 and we know the totient equals 6, we can move on to the next step, calculating the private key exponent, which is d. First, we need to understand the equation. In RSA, the private exponent d is calculated using the modular inverse of e with respect to the totient. This means d must satisfy the equation e times d mod totient equal 1. This means d must satisfy this equation where we multiply e by d and then we find the modulus against the totient. This must equal 1. We now test different values of d and check if the result satisfies the equation. That's why you see the table on the right where we try different values for d until we realize that 5 is our d. Why? Because 5 times 5 mod 6 equals 1. So the correct value is 5. Now that we have d equal 5, our private key is, as you see on the screen, we have the d equals 5 and the n equals 14. Thus, in our RSA system now, we have the public key and we have the private key. The private exponent d is essential for decrypting messages encrypted with the public key. In this example, both E and D are 5, but in real-world RSA implementations, much larger prime numbers are used to ensure strong encryption security. Next, we'll demonstrate how encryption and decryption work using this key pair. Now that we have established our public key 514 and the private key 514, let's walk through an encryption and decryption example. For this example, let's assume that our plain text message m equals 3. First, let's start by encrypting the message. In RSA encryption, we use the public key en to transform this plain text into ciphertext C using the formula shown on the screen. So the message is raised to the power E and then mod n. So this will generate the ciphertext. Substituting the values, we have the ciphertext equals 5. At this point, the message m equals 3 has been securely encrypted into C equal 5 and now can be transmitted securely. Decryption is done using the private key dn. The original message is retrieved using the method you see on the screen, C to the power D mod n. Substituting the values, the plain text equals 3. Thus, we successfully retrieved the original message m equal 3. This example demonstrates how RSA encryption and decryption work together. The sender encrypts the message using the public key. The receiver decrypts it using the private key. The original message is successfully recovered. Even though E and D happen to be the same in this small example, in real-world RSA implementations, like I mentioned before, we use much larger prime numbers. And this is what makes encryption extremely secure. RSA encryption relies on the difficulty of factoring large prime numbers. The security of RSA is determined by the size of the key, which is composed of two large prime numbers multiplied together. The larger the key, the harder it is to break the encryption. Let's examine different RSA key sizes. 1024-bit RSA. This was widely used in the past, but is now considered insecure due to advances in computing power. Factoring a 1024-bit key is within reach of well-funded adversaries, making it unsuitable for protecting sensitive data. 2048-bit RSA, currently the standard for most secure communications. It provides strong security against brute force attacks while maintaining reasonable computational cost. 3072-bit RSA, this is recommended for higher security requirements. This key size ensures protection even against future advances in hardware and cryptanalysis. 4096-bit RSA provides the highest level of security. However, it requires significantly more processing power, making it impractical for some applications. While larger key sizes provide better security, they also require more computational resources. Organizations must balance security and efficiency based on their needs. For most applications, 2048-bit RSA is considered secure and practical. However, for longer term security and protection against future computing advancements, 3072-bit or 4096-bit RSA may be preferable. As quantum computing progresses, RSA encryption may eventually be replaced by quantum-resistant algorithms. Until then, choosing the right key size is crucial for maintaining strong encryption. In cryptography, securely exchanging encryption keys over an open network is a critical challenge. This is where Diffie-Hellman key exchange comes into play. Diffie-Hellman, introduced in 1976 by Whitfield Diffie and Martin Hellman, was a groundbreaking protocol that allowed two parties to establish a shared secret over an insecure channel. Unlike RSA, which enables both encryption and authentication, Diffie-Hellman is not an encryption algorithm. It's purely a key exchange mechanism. The security of Diffie-Hellman relies on the discrete logarithm problem, which is computationally hard to solve. This is what makes it resistant to brute force attacks. Because of its efficiency and security, it's widely used in TLS, transport layer security, VPNs, virtual private networks, and other secure communication protocols. Now we will do an example to demonstrate how the Diffie-Hellman key exchange works in practice. This will show how two parties, Alice and Bob, can establish a shared secret key over an insecure channel. First, Alice and Bob agree on two publicly known values, a prime number p equal 23 and generator g equal 5, which is primitive root modulo of p. These values are not secret and they can be shared openly. In step 2, Bob generates a secret key or secret number x, and this is only known to Bob. Let's say Bob chooses x equal 4, and then Bob will compute his public value a using the formula shown on the screen, which is g to the power of x mod p. And then the result a equals 4. This is what Bob gets, and then Bob will send a equals 4 to Alice over the insecure channel. Alice generates a secret number y, and then will calculate at her side the public value b using the formula g to the power of y mod p, and then Alice will send this to Bob over the insecure channel. Now Alice and Bob both can compute a shared secret key using the values they received. So Bob will calculate the shared secret key, and Alice will do the same using the formulas on the screen after they received each other's public values a and b. Bob's calculation, how did Bob do the calculation? Bob takes Alice's public key b and raises it to his private exponent x, and the result is 18. Alice takes Bob's public key a and raises it to her private exponent y, and the result is the same, which is y. Both Alice and Bob derive the same shared secret key 18. How does this work, or why does it work? This works because both calculations are equivalent. Even though an attacker knows P, G, A, and B, they cannot easily compute the shared key because solving discrete logarithm problem is computationally difficult. This example shows how Alice and Bob can securely generate a shared secret key using Diffie-Hellman. This key can now be used for symmetric encryption to protect their communication. Now that we understand how the Diffie-Hellman key exchange works, let's take a closer look at how it happens in a real-world scenario over an insecure channel. Alice and Bob want to securely communicate over a non-secure channel, but Eve, a potential eavesdropper, is secretly listening to their exchange, trying to intercept their information. As before, Alice and Bob agree on two publicly known values, the prime number p equals 23 and the generator g equals 5. These values are openly exchanged and not secret. Alice and Bob now generate their private keys, which are kept secret. Alice picks x equal 4 and Bob picks y equal 3. Alice and Bob will use these private values to generate and exchange their public keys. Each participant calculates their public key at their end. As you see on the screen, Alice calculates A, her public key, and Bob calculates B, his public key. Now Alice sends A to Bob over the insecure channel, and Bob sends B to Alice over the same insecure channel. At this point, an attacker Eve can see the exchanged values A and B, but also does not know the private keys X or Y, because X is only known to Alice and Y is only known to Bob. Now Alice and Bob compute the shared secret key using the received public key. Thus both Alice and Bob have derived the same shared secret key, which is in this case 18. Eve's dilemma, man in the middle risk. Since Eve can see A and B, she might try to compute the secret key. However, to do so, she needs to solve the discrete logarithm problem, which is computationally hard for large values of P. Without knowing either X or Y, Eve is unable to derive the shared secret key. However, if an attacker is performing a man-in-the-middle attack, they might intercept and modify the key exchange process. This is why Diffie-Hellman alone does not provide authentication. it must be paired with additional security measures like digital signatures or certificates. This is how Alice and Bob successfully established a shared secret key over an insecure channel using Diffie-Hellman. This key can now be used for symmetric encryption to secure their communication like we said earlier. Asymmetric cryptography plays a crucial role in securing digital communications by using key pairs for encryption and decryption. RSA is a strong encryption method that also enables digital signatures, providing authentication and data integrity. However, it's computationally expensive, making it less efficient for frequent encryption operations. On the other hand, Diffie-Hellman is designed specifically for secure key exchange over an insecure network. It does not provide encryption or authentication on its own, but it helps establish a shared secret key for secure communication. So when choosing between RSA and Diffie-Hellman, it depends on the use case. If you need authentication and encryption, RSA is the right choice. If you need a secure method for key exchange, Diffie-Hellman is the better option. Understanding these differences helps in designing more secure communication systems, combining the right cryptographic techniques for different security needs. Don't forget to like, share, and subscribe for more cybersecurity content. Stay tuned for our next video and keep your data secure.